So first off in our afternoon sessions is Alessandro Oltramari. He is from Bausch, and we've had prior speakers on the symposium from the organization. He resides in Pittsburgh, and like myself, he's a fellow Steelers fan that I found out in having conversations before the symposium. And he brings a wealth of experience, and I mean it completely. He's got around 100 research publications, a PhD in cognitive science, and he'll be explaining the use of machine learning, knowledge representation, with a direct focus on Neuro-symbolic AI. So I really, truly appreciate you joining us, and the stage is yours.
Thank you. Thank you much for the nice introduction, Steve. Thanks, everyone, for being here today. I could join only briefly earlier, but I've heard a very interesting discussion going on. So yeah, today I'm going to talk a little bit about what I've been doing. We've been doing actually at Bosch research in the area of neuro-symbolic AI with application to decision intelligence, decision support systems. Okay, let me actually see if that works. Yeah. Okay, so just 30 seconds here. I mean, of course, if you're interested in what I'm doing, we can connect on LinkedIn. I also have a Bosch research expert page that you can see papers and the projects I've been working on. So my background actually is applied ontology. So I was when I was in Italy, when I got my PhD, I was part of the laboratory for applied ontology headed by Nicola Guarino, who I'm sure many people know in this context. In the last, I would say, in the beginning of my career, I worked a lot on integration between ontologies and lexical resources, WordNet, FrameNet, and whatnot. And I've been in the US for like 14 years now. First I was at CMU, and there I started working on neuro-symbolic AI, although back then we were talking about integration between sub-symbolic systems, some symbolic algorithms, and symbolic AI. And of course, these days neurosymbolism is much more fashionable as a way to refer to systems, so AI systems that merge different traditions and different approaches. Before Bosch, I actually had like a short experience also at Expert Systems, now Expert AI. It was also an important company in the area of semantic technologies. Right, so this is a little bit the agenda for today. So just a little bit introduction on decision intelligence. Also, I think I'll spend a few minutes also talking about neuro-symbolic AI, and then discuss this fairly, I would say, exoteric, topic. If you, of course, are not a specialist of emission calibration of arbitrary systems, but I'm pretty sure that the level of generalization that I have in my slides will be accessible to everybody. So yeah, so what's decision intelligence? So in general, it's considered a field that helps support and augment and automate decisions of humans by connecting the data with the outcomes and the decisions made by experts, technicians, operators, or users. And it's a combination of different methods. Of course, because it's about decisions, it needs to incorporate the capability of modeling how humans, make actionable knowledge and are capable of projecting beliefs, desires, intentions, emotions, even right in their decision-making process. And so, of course, when we talk about a system that replicates that type of capability, it's an integration of knowledge graphs, machine learning, so algorithms like rule-based systems that are capable of, I would say, projecting dynamically knowledge into a decision space. And of course, it's not just one and done kind of process, because as every decision has a consequence in the real world, that consequence, which can be a consequence in an environment, indoor, outdoor, or can be, a decision in a business situation, the outcome of the decision can also be used as a feedback to improve the system over time, right? So where you can, of course, see there some mechanisms like reinforcement learning be very useful. Now, the difference between AI and DI is that, when you have AI-based analytics, you just have access to a large amount of, say, insight on a large amount of data. But when you use decision intelligence system, you are also trying to connect the analytics to strategic decisions and to, again, what I just discussed earlier regarding ways in which, as humans, we take into consideration the state of the world and perform actions to change it or to execute some tasks. So the benefit is that, as you may imagine, in a very data-intensive scenario, with a system like that, with decision intelligence systems, you can reduce the time of executing an operation or a set of operations. You can reduce errors. And also, as humans, through these systems, we are provided with much more situational awareness. Right. So, and this is a fairly new actually area. I think before a couple of years ago, there were not even, say, the word decision intelligence didn't mean much. Now, when you look at that, you can basically see three basic distinctions, three basic ramifications of how decision intelligence can be implemented and realized in the real world. The simplest level is decision support, where the decisions are made entirely by the humans, and so what machine provide are just some forms of generalization over the data that can be alerts, can be analytics, ways to visualize and explore data. So, for instance, some systems that visualize knowledge graphs can be seen and can be called decision support systems. Decision augmentation is more like when the system is also providing, there are recommendations and predictions, and it's this point is so at this level is up to the human to make the final decision on the basis of these recommendations. And I would say decision automation is, if you want, is what is L4 in autonomous driving, right? So this is a system that decides by itself and without any human intervention, where it's not completely true that without human intervention. So, as in a self-driving car, hopefully you add the capability as a human to step in if needed. In the case of decision automation, the human is always present to analyze the risk and to monitor, as the decision is affecting the real world. And by the way, feel free to ask me a question if you want in the presentation. We don't have to wait for the end. If they are brief, otherwise we can discuss later. So when we look a little bit at the landscape of this decision intelligence, topics vary a lot, right? So you go from a market decision making, so like a more business oriented processes, to something that can be very helpful in the area of manufacturing, like root cause analysis in manufacturing facilities, power forecasting, and whatnot. Now, when we look also at the actors around there, there are, this is actually these little pictures are like a combination of providers of decision intelligence systems and also users, like Unilever. IBM, I would say, is very strong in this area. Traditionally, has been very strong. Google, of course, is stepping in as well. Alibaba is a decision intelligence lab where they are working on some of these domains and use cases that I list on the left. And also a recently formed startup in UK, Rainbird, expressively use Neuro-symbolic AI as part of decision intelligence systems there. So what we work on at Bosch Research, at least my team and I, is the area of decision augmentation through Neuro-symbolic AI. So I'll be quick on neuro-symbolic AI. I'm assuming that there is some level of familiarity across the audience, but again, feel free to stop me if I'm too quick. And so, right. So this is also important for Bosch, right? So this is not just an academic exercise to see the importance and to understand that for some hard problems, one solution is not sufficient. But this is also something that we have derived as a requirement from Bosch. So Bosch has vast amounts of highly valuable data that span from production history, sensor generated data set, and so on, and of course a lot of domain knowledge that we collect through best practices, technical know-how, manuals, and so on. So making use of these important assets is key for things like automatic distillation of insights from data to automatic decision support. And this again has an impact on cost savings and services and products. And when we look at the state of the art, or we look at industry, in many cases, AI methods employed in industry are either data-driven or knowledge engineering-driven. Only a few examples exist combining the two. For many reasons. Also, some reasons are due to infrastructure. So not many systems out there can merge these two levels of information processes. Now, there are benefits and downsides, I would say, in using either data-driven methods or only knowledge engineering methods. Or from one side, data-driven methods excel in pattern recognition, but can also be easy to fool and often violate constraints. And knowledge engineering methods, on the other side, excel in precision and explainability because they are part of the systems, by default. But as we know, we don't scale well and overly top-down in most cases. Some examples, and I'm not going to delve much into the details here, but so what does it mean that data-driven methods are easy to fool? Well, let's just focus on, we know the examples of course, adding stickers to a stop sign, and then that actually drops the accuracy of computer vision system that otherwise would have been able to recognize the stop sign very easily. And other things like that happens when you implant on pictures different objects of the same type, like a tennis ball versus a soccer ball, which is out of context, but that degrades the performance of the system to identify the color of a dress in this case. And there is a famous paper, The Elephant in the Room, which is about implanting elephants in the test set of a benchmark on computer vision, where if you have a floating elephant in your living room, which otherwise would have been recognized with 100% accuracy, the objects that are in it, with implanting an elephant from the training set, degrades the performance enormously. What is more interesting from our perspective is the type of easy to foolness, if I can say something like that, on the decision aspect. So you may have read something about this article came out on Wired a while ago on child abuse prediction model that actually were deployed here in Pittsburgh. And so the problem there was that if you use unbalanced data sets to train your models, for instance, from areas of high poverty in the case of child abuse prediction, then using features like how many public resources a family uses, you have a system that is basically biased towards, or I would say, against minorities. And so it predicts a lot of child abuse because the features that we use are typical features of poor areas. This, of course, created a big problem. And we hear also a lot about using AI in court system. That also is very critical. And so these are some of the real risks that we are running here, more than AI taking over. Right. And so for knowledge engineering methods, they don't scale well, typically at least. So how it started, we are all familiar with this. Knowledge engineers implement a semantic model or an ontology. So the T-box, nobody uses T-box anymore, but that's what it is, an ontology. And then data from databases are then linked to the ontology, and then you create a knowledge base or a knowledge graph these days. And then you have inference engines on top of it, rules and so on. So how it's going, and of course, we know that Psych, for instance, is one of the examples of a system that has been developed for many years, and ends up with 25 million assertions, and you can interpret an assertion as a triple, right? So now, of course, there are ways there have been ways, and developments to bootstrap the creation of knowledge graphs. Let's think about the Google Knowledge Graph, which didn't take like 40 years to get to much more triple numbers that higher triple numbers that we have in Psych. In this case, we have I think 8. Well, this is updated to last year, but 800 billion facts, so triples. And then we also here using LLMs as KGs. Yes, but of course, human in the loop is always required, especially when we look at LLMs, because they can create hallucinations and they make mistakes. And also, although things are very fluid, but typically they are frozen, right? So they are reflecting the data up until a certain year. Now, this process is being improved as well. But there is also the issue that using an LLM for getting a correct answer is far from optimal, as we know in many use cases. And so Neuro-symbolic AI, again, is the combination. You basically try with this virtuous cycle to capture the benefits, to maximize the benefits and minimize the problems. So explainability, scalability, correctness, robustness, and generalizability. And yeah, again, here, of course, we are active as Bosch. IBM, again, is very active in this space, NVIDIA as well, Alibaba. So very important topic. So now, looking a little bit in the use case, right, of the ECU calibration of powertrain systems, so electronic control unit calibration of powertrain systems. Let me actually give you a little bit of introduction here. So the ECU calibration of powertrain system is the process of assessing whether, given an engine model, for instance, a BMW something, that engine can achieve a target emission standard. And this is called project feasibility assessment, or PFA, as you may see also in the next slides. So emission calibration, and then so these emission calibration standards. So there are many of those across Europe, US, China, different types. So I think in Europe soon there will be Euro 7. Right now they have Euro 6. And so what these emission standards are basically some thresholds of concentrations of pollutants like CO that are admissible in that particular territory. But when a powertrain system, a Bosch powertrain system expert receives this engine with the task, assess the feasibility of this engine, for instance, in the Chinese market, and so meaning that we need to comply to some numbers with respect to the concentration of 7, 8, 9 type of pollutants. The task is very data intensive, because a vehicle comes with I think more than 100 different specs / attributes. For instance, number of cylinders, rated engine torque, rated engine power, the presence of absence or certain sensors, and these come really to the point that they are in the order of their hundreds. And then, of course, testing an engine, for the test to be comprehensive, you need to test under different conditions, different temperatures, different type of terrains, of course, in a testing field, in the real environment, in the lab, so only the engine. So this is a very labor-intensive, error-prone set of tasks. And up until, I would say, a couple of years ago, this was a task completely where the reports were completely done by hand. So think about a big spreadsheet where the different readings of the different sensors were recorded and correlated with dozen and dozen of different tests. So at the end of the day, of course, it's up to the human to make a decision. So this is a feasible project under this market, so green. Is it not feasible, so red, or I don't have enough information, so I need to go back to the OEM, or I need to run more tests, yellow. Automatizing this process by our estimates, not our estimates, but more like by our business unit estimates, can get to a cost saving of around 4.5 million and reducing error. So what we did actually is to replace this huge spreadsheet with a system that incorporates a knowledge graph that can represent all the projects and project data. And on top of this, we use machine learning algorithms and rule-based reasoning to perform some operations that we introduce in a second. Where what is important is that, and I didn't mention it earlier, so if this is so data intensive, how were the experts doing it, right? Well, they were coming up with very clever heuristics to basically identify important core attributes and correlate them with important tests in the overall set of all the tests and all the attributes. And so we were able to capture, by working with our experts, to capture a set of rules, fairly complicated rules with many conjunctions, conditions, and conjunctions in the body of the rule, but that actually reflect the type of heuristic, which is important if you want to gain the trustworthiness of the system. So this is more or less the architecture, and we have also published a couple of papers. AAAI and somewhere else that I can recall right now. So if you're interested in more details, I can also provide links. So we are using as our central, I would say, knowledge graph framework Stardog. And in particular, we connect Stardog with a proprietary database we call HiCase. It's an Oracle database. So we use what is called a virtual graph in Stardog that is nothing but a list of mappings from the database to the schema or ontology that we use to represent the domain. So this allows pretty much to minimize the materialization of the data, and also allows us to always have fresh data out of the database. So if new projects come in, we don't have to take the projects and create a pipeline that takes the projects and materialize them in the knowledge graph. But this is actually automatically evoked or when a query runs against the knowledge graph and basically using the most updated version of the database in the backend. On top of this, we have, of course, Sparkle queries that reflect some of these rules that I was mentioning before. And then we use also Stardog machine learning. In particular, we use the similarity and regression models, linear regression model, in the way that I will just describe in a minute. On top of this, we have a very simple, for now at least, user interface where we allow the experts to search, to inquire the system, but also to get recommendations out of the system. So this is more or less the kind of workflow of the functionalities that we have, and yeah, there's not much else in this I would say user interface that would have required a magnification here. So basically, you select a project in a variant. Again, project and variant here means an engine model, BMW Mercedes-Benz or Fiat something. And then, of course, these may come with different variants. And once you have that, which is this input project level, you have two main ramifications. So similar projects and guest suggestions. And I will describe you in the next couple of slides what this means. So in the similar projects, very simply and very intuitively, right, you are basically able to assess if this new project that comes in has anything to do with projects that you or the expert has assessed in the past. And this is very likely, of course, because it's very rare that a completely new model of an engine gets implemented, gets built. You always have to deal with power, with torque, with cylinders, at least when we're talking about combustion engines. And so there's always a level of similarity that we can output for the expert. And of course, together with a similar project, we can also show what were the assessments done for the similar projects, such that can become a sort of compass for the experts to understand where to go. In other situations, though, we can provide directly some suggestions to the expert. So if all the data about the projects are there, we can just basically fire. So what you do is you trigger rules that satisfy the engine attributes. And out of those rules, you get a rating suggestion. So again, feasible, not feasible, or I don't have enough information. In the case of complete data, all the information is there. So you're always going to have an output that is green, yellow, or green or red. But if the data are incomplete of the project, there are two possible situations. They are incomplete because the project manager of the OEM failed to transmit some part of the data. Let's assume that they forgot to put that there is a certain number of cylinders. So at that point, the system doesn't do anything because this is a problem of knowledge management. So we need to go back to the OEM, fill that information, and then provide the rating. But in other cases, and this is quite often actually the case, because the number of tests are so many, in many cases, projects don't have a complete information regarding all the concentrations, measurements of pollutants across different conditions. And so what happens in that case? Well, in the past, nothing much, right? So either you run those tests or you really make a decision on the basis of the information you have for the tests you have run. But in our case, using machine learning, particular prediction models, we were able to actually train some algorithms to predict concentration of different pollutants based on the characteristics of the engine. And as you will see briefly in my second last slide, I think we achieved a very high accuracy. So in this way, what we can do actually is complete the knowledge graph with the data that are missing. And once we have reinstantiated this, we can get a prediction as if the data were complete. And I pretty much explained how this workflow works. This is just to show you also that our system is really distributed in the cloud. So we have Stardog instance right now running in our headquarters in Renningen and in Stuttgart, so Germany. And the database right now resides in India because most of our combustion engine experts work there. So yes, not super readable, but I also had to put some graphics on top of the brands of the projects because, of course, this is proprietary information. But you get the idea that you basically have like some ratings of project similarity. So given a project as an input, you get a ranking of projects that are most similar and their status. In this case, we have the two projects that are 62, so 62% similar to the original one, to the one given as an input, and they are green. When the similarity goes down, they become yellow because in some cases, this means that these projects are not reliable for making a decision for this one in particular. And then we also can see, given the input and the output, and because the similarity of course is not one, we can see where are the differences. For instance, and I also can see myself here, but this is the value of torque, which is different, like 250 versus 93 Newton per meter. And these are different certificates, Euro 6D and Euro 6D temp evap, which of course are, very technically, very technical in this domain. And here you also see the concentration of the pollutants, CO, NX, and so on. Yeah. And so this is actually what happens for the get suggestions. So the difference with get suggestion is the following, that the way we build the system, the rules are kind of materialized. So these are Sparkle rules that are materialized in the knowledge graph. And because we are using Stardog ML, also the machine learning algorithms are materialized through insert queries into the knowledge graph. So in this case, actually, we are not doing anything externally with the database. We are just using, so given an input, you can retrieve the suggestions just by running queries on top of our knowledge graph. Where again, queries here is a combination of traditional Sparkle queries, machine learning models trained using Stardog ML, which also are insert queries, or at least this is how you train them, and then you can just select a bunch of different properties to get the prediction, and rules that are also represented here as a Sparkle rules. So this is an example, a screenshot from the two types of visualization that we have in the system. One being in the form of table, where you can see, okay, for pollutant CO, the status of this project is green, and then we have an explanation which says the project is green because it's a China high emission standard and the predicted value of CO. So this means that we have actually used here our regression model to predict the value of CO. And in this case, we see that is inferior than 350 milligrams per kilometer, which is a particular threshold for that emission standard, and so on. And then we can also say, okay, this suggestion comes from the machine learning because we have introduced this value that is predicted. It's also important to see, say, in many cases, there is not only one explanation of why a suggestion has been provided. And here we show that this final explanation depends on two other facts that have been observed. One is actually the prediction made with the machine learning algorithm. In this case, we can see the value that is there, plus the confidence which we get out of the Sparkle query run over Stardog ML. And also we get the other part of the explanation where it says, okay, this particular project is a project for the Chinese market, so with the emission standard China 6B. And as I told you before, when we look at the precision of, so the accuracy of our predictions, is at least for CO and PN, we are very accurate to the point that we get to above 90% when we test our predictions against the average values that are assumed for those particular brands of engines that we have in the database. Right. So some final considerations here. So Neuro-symbolic AI is really a key to decision intelligence, and not only for our use case on emission calibration, but in general. For this particular use case, and when we look at the different dimensions that the different factors that we can associate with Neuro-symbolic AI. So explainability. So of course, this comes out of the explicit data semantics that we have associated with project attributes. The correctness comes out of the deterministic rule-based reasoning that we have So the rule engine that we are using here at the basis of the classification green, red, and green or red, where yellow again means that there is no recommendation by the system, either because there is some data missing, or maybe because there are competing rules that fire. And these may actually provide concurrent interpretations. So for one rule, a project may be feasible, and for the other may be unfeasible. And this is totally fine, because this is also, I would say, a consequence of how these rules, so these heuristics, have been formalized with our experts. It deals with the fact that rules and engines change over time, and so some things have to be adapted. So at the end of the day, this is why this system is about augmentation, not automation, is the expert's call to disambiguate if two competing rules are firing. And so yellow here is actually very informative as well, to retrain the system in the future, to improve the system in the future, even to remove some rules or build new ones. Currently, our system is based on a database of 15,000 projects or so. And again, this is our virtual graph covering all these projects. But we don't have any problem in terms of scaling up that in the future. It's robust because we have actually run experiments across different brands and models, and also it's generalizable. We claim, although we haven't proved that at full yet. But combining knowledge graphs, rules, and machine learning is in general a solution that can be beneficial for any type of domains and problems that require a decision. Because again, rules can express how we encode our own heuristics to execute a task. Knowledge graphs represent the knowledge base that we can encode using computational systems like knowledge engineering frameworks. And machine learning and neural models in general, because there are so many applications that we can expand and advance thanks to sub-symbolic systems. In fact, some of the future work we are currently contemplating, but in some cases we have started already. So one is actually a very derivative use case. So the same problem of calibration, but of electric vehicles. Now, in the case of electric vehicles, of course, the problem is not about the emissions, right? Because at least when you consider fully EVs, they don't have any problem with emissions. They don't have any emission. But there, the problem could be, for instance, maybe to predict if that model is feasible within the range of a certain battery consumption, stuff like this. And then, again, I mentioned it before in the landscape of use cases and domains. So root cause analysis in manufacturing is also a domain and a problem that naturally fits within the realm of neuro-symbolic AI for decision intelligence. And I would say the big problem of compliance in general with the regulation. And this is completely different from, of course, manufacturing. Like, for instance, let's consider GDPR, right? GDPR in Europe, it's a very complicated, fairly complicated set of rules for privacy and security. Now, to make sure that your operations are compliant with GDPR, of course, and you want to do it at scale, you really need a decision intelligence system. And then being able to formalize and implement rules that reflect those regulations is definitely an important step for making this type of tasks much more fluid and much more dynamic, I would say. So I think we are running out of time, and I'm done. Just wanted to end with this slide and picture that most of you probably have seen already. So the Gartner prediction and expectations for the following years. And interestingly enough, among the different topics and disciplines that we see in this chart, only neuro-symbolic AI and generative AI, of course, so LLMs and stuff, are seen as innovation triggers. And this is, I think, it's a good conclusion also for this talk, because I haven't even touched upon the problem, I would say more than a problem, the opportunity of integrating neuro-symbolic AI with generative AI. So the capability of using some of these techniques together with large language models or multimodal models that can improve a lot also the experience that the user or the expert have when using decision intelligence systems, because that becomes more natural since it can be implemented through natural language, and in some cases can also provide additional modalities like vision. But this, of course, it's also more a matter of future research and development rather than something that is ready right now. So with this, thank you for listening, and we can open up the floor for questions.
Very good. There's one here. Why did you choose to create rules as Sparkle queries instead of using reasoners or inference?
Right. No, that's a good question. So, and we are not ruling out, no pun intended, to do it in the future. Currently, the expressivity of Sparkle rules is for us sufficient to capture the type of heuristics we have considered. But as a matter of fact, I've already started working on a probabilistic reasoning system, so where we also can express a little bit some weights and have as an output a distribution which is much, I would say, in some cases, especially when the rules become more complicated, it's performing much better. It's more effective and more efficient.
Very good. Steve, I know you had one. Go ahead.
Yeah, question more operational. And I know that we talked earlier about a great deal of the semantic experimentation starts in research and innovation labs. And I was seeing if you could go into a little bit more depth as to how, the Bosch research engages with business or technical SMEs and kind of giving it more practical realization. How does that process work?
So well, the example that I provided today is completely internal, in the sense that as Bosch Research, we interact with different business units in the constellation of business units of Bosch. In this particular case, we interacted with powertrain solutions. So the way we started, for instance, this project was by analyzing the pain points that our business unit was having in this particular task. And of course, we also did some dissemination work to make our business units aware of the type of solution we can provide to, I would say, tackle problems of this nature, where there is a decision in the downstream task, and the availability and the dimension, the scale of the data is such that you need to introduce an AI-based solution to deal with that type of complexity. In some cases, we also go out in the world, but we always do so as corporate research. I would say 90% of the times we go hand to hand with our business units, because at the end of the day, you want them to transform a prototype into a product or into a service. And so that's how we provide the knowledge transfer, the prototype transfer, we consult, but at the end of the day, that becomes an output of our business unit. Of course, from an external perspective, it's still Bosch, but that's how we operate a little bit inside.
Yep. And so how does that, and you mentioned that you have 150 projects, how does that collaboration work to for those that maybe have the problem, know that you might be the right group to get in touch with?
Well, I mean, it's complicated, right? Because especially in a multinational corporation like us. So I wouldn't say that there is a magic bullet or there is like a one procedure that we use. We have many opportunities during the year, typically, to pitch our ideas, to meet with business units, with the heads or representatives and staff of different business units, to sit together and go over, different type of problems, and so pain points versus offers and solutions. So this is a process we tend to do pretty continuously over the year, and then there are the serendipitous situations where there are contacts either within a region like North America, or across regions when we visit Germany, where our headquarters are.
Yep. So you would call these more or less just innovative think tank sessions or something like that?
Yeah, we do call them innovation workshops most of the times, strategy workshops sometimes. Yeah. So.
Yep. Wonderful. Well, very enlightening. Thank you again for joining us this year. Appreciate it. We'll just move on to our next session. And if there's any further questions, you'd be willing to take those offline as well?
Absolutely. And thank you again for inviting me.
Yeah. You have a great day. Thank you.